Light sleep. Stage 1 of non-rapid eye movement sleep, also known as N1, represents the initial phase of the sleep cycle that serves as the transition from wakefulness to sleep. Typically, N1 lasts for approximately 1 to 7 minutes, constituting about 2 to 5% of the total sleep cycle. During N1 sleep, muscle activity decreases and eye movements become slow and rolling. Breathing and heart rates begin to slow down, and body temperature drops slightly as the body gradually disengages from the external environment. Brain activity during N1 transitions from alpha waves, which are associated with relaxed wakefulness, to theta waves. Theta waves induce a gradual decline in sensory awareness and attentional focus that eventually lead to proper sleep, but can also make you more prone to brief episodes of microsleep, where you momentarily lose awareness without fully realizing it. Functional imaging studies have shown reduced activity in the prefrontal cortex, a region associated with logical reasoning and decision-making. However, the brainstem and thalamus, the body's information relay system, remain partially active, allowing for a heightened sensitivity to external stimuli, hence why people in N1 sleep can be easily awakened. This heightened sensitivity is a protective mechanism allowing people to respond quickly to potential threats in their surroundings, and likely allowed early humans to remain alert to predators or other dangers while sleeping in an unprotected environment. A common phenomenon during N1 sleep is the occurrence of hypnic jerks, which are sudden, involuntary muscle contractions that may cause a person to jolt awake momentarily. They are often accompanied by a sensation of falling and are considered a normal part of the sleep process. They result from the brain misinterpreting muscle relaxation as a sign of falling, triggering a reflexive response to catch oneself. Another common experience during N1 sleep is hypnagogic hallucinations, which can involve visual, auditory, or tactile sensations, such as seeing geometric patterns, hearing voices or music, or feeling a sudden presence in the room. Unlike dreams, which occur primarily in REM sleep, hypnagogic hallucinations tend to be more fragmented and influenced by recent thoughts or external stimuli. Moderate sleep, N2, serves as a bridge between light and deep sleep and comprises about 45 to 50% of total sleep time. Compared to N1, where people can be easily awakened due to heightened sensitivity, N2 represents a more secure phase of sleep. The brain remains aware of the environment but reacts less readily, ensuring that minor disturbances, such as distant sounds or slight changes in temperature, do not cause wakefulness, allowing the body to prepare for the deeper and more restorative stages that follow. During N2, heart rate and breathing become more regular, and body temperature decreases. Muscle activity further diminishes, and eye movements cease. This stage introduces a notable change in brainwave activity, with theta waves still present and in a larger concentration, but now accompanied by two distinct features: sleep spindles and K complexes. Sleep spindles are rapid bursts of brain activity lasting 0.5 to 3 seconds, which protect sleep by reducing sensitivity to external noise. Higher spindle activity is associated with better retention of newly acquired information, and people who experience more sleep spindles during N2 have better memory retention the following day. High stress levels have been shown to decrease the number of sleep spindles, meaning that people under chronic stress or anxiety struggle with retaining and recalling information. K complexes, on the other hand, are high-amplitude waves that occur spontaneously or in response to external stimuli. They serve as a precursor to deeper sleep states, ensuring that brief sensory inputs do not disrupt sleep, while also acting as a gateway for memory consolidation, synaptic plasticity, and information processing. K complexes are a major factor in healthy human sleep and have been linked to the synchronization of neural activity between different brain regions, particularly the thalamus and cortex. One factor that can interfere with N2 sleep is caffeine consumption too close to bedtime. Caffeine can delay the onset of N2, prolonging light sleep and reducing overall sleep efficiency, which is particularly concerning because an extended N2 stage at the expense of N3 disrupts the body's ability to fully recover overnight. Deep sleep. N3, also called slow wave sleep or deep sleep, is the most restorative phase of sleep and typically begins 45 to 90 minutes after falling asleep. It is marked by delta waves, which are high-amplitude, low-frequency waves that help slow down brain processes. During N3, the body experiences its deepest state of relaxation. Heart rate, respiratory rate, and blood pressure all decrease significantly. Muscles are fully relaxed, tissue growth, cell repair, and immune system strengthening are enhanced, and growth hormones are released in large quantities, which are essential for muscle recovery, metabolism, and overall physical health. Similarly to N2, people who get more deep sleep have stronger neural connections and memory transformation. This memory transformation is facilitated by the hippocampus, where it communicates with the rest of the brain to transfer information for long-term retention. Naturally, people deprived of deep sleep lack this, and their brains struggle with recall as a result. In young adults, N3 can make up 20% of total sleep time, but this percentage decreases over time. This decline begins as early as the late 20s and continues progressively with age, with deep sleep decreasing by approximately 2% per decade. By the time people reach their 50s, they may experience only half as much deep sleep as they did in early adulthood, and by the time they reach their 70s, N3 sleep may be nearly absent. During N3 sleep, the glymphatic system, the body's waste-clearing mechanism, exhibits a spike in activity, allowing cerebrospinal fluid to flow more freely through brain tissue. Because the elderly get significantly less N3 sleep, glymphatic activity decreases, increasing the chance of abnormal proteins, such as beta-amyloid plaques and tau proteins, to form, key biomarkers for the cognitive decline of Alzheimer's patients. When the transitions between N2 and N3 are not carried out properly, the brain enters a mixed state where motor functions and autonomic responses are partially active, but full consciousness remains suppressed. As a result, parasomnias such as sleepwalking, night terrors, and bedwetting can occur. Parasomnias are most frequently observed in children and typically decrease with age as the percentage of deep sleep lowers, but can persist into adulthood, particularly if there is a genetic predisposition or underlying sleep disorder. Since the brain remains in a state of sleep, people experiencing parasomnias often have no memory of their actions upon waking. Rapid eye movement sleep. REM sleep is a critical stage of the sleep cycle, occurring multiple times throughout the night and constituting about 20 to 25% of an adult's total sleep duration. This stage typically begins about 90 minutes after falling asleep and extends in duration as the night progresses. It is also the stage most strongly associated with vivid dreaming, where the brain comes up with strange, surreal narratives that often lack clear logic or structure. Unlike the previous stages of sleep, where the body is in a state of relaxation, REM sleep is marked by intense brain activity, rapid eye movements, irregular breathing, and increased heart rate. This state is often referred to as paradoxical sleep, because the brain is highly active while the body remains largely immobile due to muscle atonia, which prevents people from physically acting out their dreams. Occasionally, a phenomenon called sleep paralysis can occur, when the body fails to transition out of REM sleep. In this state, atonia continues, while the brain remains aware of its surroundings. As a result, elements of dreaming may leak into wakefulness, resulting in lifelike and tactile hallucinations, such as a shadowy figure in the corner of the room, or an intense pressure on the chest. During REM sleep, the prefrontal cortex shows reduced activity, resulting in a diminished ability to evaluate dream content. This suppression contributes to the fluid, narrative-like structure of dreams, where events often unfold without clear cause and effect relationships. Conversely, the amygdala, responsible for processing emotions, exhibits heightened activity, which, in combination with prefrontal cortex suppression, can potentially transform dreams into emotionally distressing nightmares. This unique pattern of brain activity during REM sleep allows for boosted creativity and problem-solving in ways that waking consciousness often cannot, which is why many creative breakthroughs and insights have been linked to dreams. Those who experience lucid dreaming exhibit increased activation in the prefrontal cortex, enabling them to recognize that they are in a dream state and can exert control over the dream's narrative and environment. When people are deprived of REM sleep, the amygdala becomes hyperactive, leading to exaggerated emotional responses to negative stimuli. The connection between the amygdala and the prefrontal cortex becomes impaired, resulting in a reduced ability to regulate emotions effectively and subsequently making people more prone to impulsive reactions and poor decision-making under stress.